So hello, everyone. Welcome. I know that dressed like this, I look like a marketing guy, but I can guarantee that this talk is going to be actually pretty technical. Just to understand where we are, how many of you have worked in the past with Cord? How many of you have experience with the platform? 50%, I will say. For the other 50%, I think if you're coming on board now, that it's a really great moment to come on board. The platform made some major step forward, and the developer life and the developer cycle get much faster, much better, much nicer. So before talking about how the development workflow look like, I want to make sure that we are all sharing some concepts. Sorry, my laptop went on standby. So we'll talk about Docker, Kubernetes, Helm. We'll make sure that we are all on the same page. And then we'll go through a quick demo on what is a developer everyday life. So we're doing something. We're creating a new feature. For sure, it won't work the first time. So we're going to introduce some issues in the code. We'll find it. We'll fix it. We'll test it. And we'll deploy it on a pod somewhere, and we'll check that everything is now working as expected. So everyone really knows what is Docker, because it has been the buzzword in the last like 5, 6, 7 years, but sometimes I still think that there are a little confusion around the terminology and around the concept in it. So we can define Docker like Wikipedia does, performs operating system level virtualization. What does that actually mean in practice? Docker let us bundle our application into a container together with the tools, library, configuration, everything that the application needs to live. And it takes us of the communication between this application for us. So in short terms, it makes a developer life much, much easier. And more than that, makes an operator life much, much easier. So as we know, we have images and containers. What is the difference between the two? We all start the journey with some code that we have written somewhere, most likely on our local machine. We take this code, we invoke a command, docker build. This will give us an image. We can think about this image as a VM image, like a .osi for VMware. And what do we do with this image? We can spin it up and have a running container, and we can have multiple instances of that. And then we can have configuration files that are mounted in those containers and shared between the two. So we know what is an image and what is a container. Now we said we start most likely building an image. Where does that image live? When we build it, it lives on the same machine where we built it in the Docker daemon. That basically means somewhere hidden in our file system. If we're running on a Unix-based file system, is var lib docker blah blah blah. Once we have it there on a development machine, we most likely want to ship it to a production machine, because we need to run it somewhere so that our customer can use it. And in order to do that, we need to get this image in the Docker daemon of the production machine, and then we can spin up the container. How can we do that? This is where most of the confusion between Docker images, Docker build, Docker run containers comes from. The way to ship images from one place to the other is the Docker registry. The Docker registry is basically a catalog of images. Like if it was a catalog of products somewhere on the web, I go there, I choose the one I want, I download it, I run it. And we have basically two different types of registry. Public registries available over the internet, and private registry that are running most likely on premises on our deployment or somewhere close to it. So how do we get all our stuff? Source code, we build the image, is local. Now we need to ship it. We need to get it to a Docker registry. We have basically one command that lets us do that. That is Docker push. We may need some time to invoke a Docker tag command, but we'll talk about that in a few minutes. And once we have that, once our image is somewhere that bot machine can reach, we just need to invoke a Docker pool to get the images on the destination machine. We have it running on the local Docker daemon, and we can start it. All clear so far? Any question? Good. How are our images called? What are the pieces that compose the name? So we start building some source code, for example, the core of XOS, and we invoke the command docker build -t open chord /XOS core column latest. What do these pieces mean? We identify the organization, the project name, and the project version as part of the build. Now, let's say that we have two different registries where we want to push that images. One is a public one on Docker Hub. One is running somewhere on a private machine in our network. We can introduce this prefix to the name of our images that is nothing but the address of the registry. So now we want to push to Docker Hub. We just invoke this simple command with the plain name. We want to push that same image on our private registry. This is a very common workflow for development. Before publishing an image out in the internet, we want to try it on our test setup, and we want to put it somewhere private. We tag it. We prefix the images with IP address and port of the registry. If the registry has a DNS associated to it, even better. And then we push the new image using the full name, including the registry. How do we tag images? We've seen that the last part of the name after the column, it's nothing but the tag. One of the biggest confusion in Docker is the latest tag. Most people think that that is the last released version of a project. Most likely, latest is tracking the master branch on Git. It gets rebuilt every time someone makes a commit, so it's a moving target. You have no guarantee that the latest you get today is the same latest you'll get tomorrow. Then we have tags that tracks branch. These are other moving targets. They are generally two versions composed by two numbers, major and minor. And then we finally have releases. They are generally bound to tags in Git. They won't move in time, so anytime you download a 1.6.0, 1.6.3, 1.6.x, you'll get exactly the same image. And remember that, generally speaking, semantic versioning is your friend. So if you are using API that are in the 1.6 version, most likely they'll work with 1.7. Now, we set the base with Docker. Kubernetes, it's a tool that helps us managing Docker container. It helps us automating deployment, scaling, and manage the life cycle of the container. Basically, it runs in a cluster. You can also run it in a single node if you want. But the cool thing that it gives us is that we don't have to worry anymore where our containers are running. We had a great introduction this morning at the keynotes about Kubernetes, so I'm not going to spend much time on it. It helps us managing mounting files, because in the moment we're running container across a cluster, we don't know where they are. if we had to do this, we had to put our configuration file in every single node in the container. We need to make sure that the updates are consistent across all the nodes. And it also handles networking through this cluster, through the container, so that we can just reference other application by the service name we had decided for them. And Helm, finally. This is the way we package application in Cord. We provide a set of charts, and Helm defines itself as the package manager for Kubernetes, because most likely, in these days, one application is not composed by a single service. It's probably composed by multiple instances of multiple services that together deliver you a feature. So you need a way to package them. And Helm let you do that, easily do that. You can define these application templates. You can have variables in them, so you can configure them. And the coolest feature I will say is that it lets you easily manage upgrades and scale of this application. Now let's see a very small example that I took from one of the Helm charts we have in Cord. We can see in the top part the definition of one of the services we want to run. In this case, it's Sonos. As you can see, we have a template language that is very, very similar to Jinja. It's actually the Golang templating language. And we define placeholder in that. We define the name of the image that we want to use and the tag. In the same way, we define these things called image pool policy. Of course, we have default values in Cord to use them. But as a developer, as an operator, you may want to override. So we see here the default values. You may want to use a custom version of Sonos. You may want to use a custom version of it. Now let's talk a little bit about this image pool policy that is one of the key concepts if you want to operate a Kubernetes cluster managed by Helm. We have basically two choices, always, if not present. What are the differences between the two? Always will force the Docker daemon to always download the image, even if it's already present on the machine. Now, this doesn't mean that every single time if our image is 1 GB, it will download 1 GB of data, because Docker has a pretty good caching system. So what it means is that Docker will be forced to contact the remote registry, check the difference between the image it has locally, the image it has on the registry, and download only the delta between the two. Now, when is actually the Docker daemon going to contact the registry? Every time we do an Helm install, every time we do an Helm upgrade, if something in that service definition has changed, and every time we delete a pod manually on Kubernetes. Every time we do a command like kubectl delete pod, Kubernetes will actually restart immediately that container for us. So you can immediately see that having the pool policy set to always is a very good case for development, because I don't need to redeploy anything. I don't need to restart anything. I upload a new image on the Docker registry. I kill the container. I get the new version running. So the pros of this approach is that we always get the latest available imaging. The cons, the danger of this, is that if we are using an image that can move over time, we have no guarantee that the image we got on one node is the same we'll get on the other node. This can be OK for development. Maybe it's not ideal for production or trials. If not present, it's a little smarter than always. The Docker daemon just check, do I have this image? Yes, good. I'm going to use the one I have locally. No, I'm going to ask to the registry if it's there or not. And this happens with the same set of commands we have seen before. What are the pros and cons? It's faster. You download newer images that you are not expecting. It's very useful if you are running a single node cluster development environment, you build the images directly on that machine. You don't even have to have a registry to run your development code. What are the issues with it? If it's a moving target and you want to follow it, it will not download a new version. Depending on the case, this can be good or bad. The trickiest part is that when you restart a container in Kubernetes, you do kubectl delete pod, you have no guarantee that the container will restart on the same node on which it was before. So you can expect that you'll get the same image. Instead, the container has been allocated to a new node, and you'll get a different image and different result. So at a very high level, don't take this as a Bible, because there are many needs and grits in it. But I will suggest to use for development on a single node the if not present policy. For development in a cluster, always pull images so you're sure what you're getting. Production and trials, always pull images with a big exclamation mark. Don't target moving charged if you're running trials. Any questions so far? So this is a good question. The difference between a Docker container and a Kubernetes pod. A pod is in Kubernetes is a logical entity that represents the minimal building block of an application. You can put multiple Docker containers into the same pod, and at that point, Kubernetes will guarantee for you that they'll be deployed on the same node on the cluster. You generally bundle together containers in a pod if they exchange a lot of data between the other, and if you need to have a very low latency between the two, because if they are on the same node, the communication will go through the Linux socket. It won't even go out to the network. Sorry? So Kubernetes was born to run Docker containers. There are Kubernetes plugins that let you run VM in different ways. I think you can run Mesos container on top of Kubernetes, but I've never tried that myself. I will say that regardless Kubernetes allow you or not to manage different kind of containers, Docker is the mainstream use of Kubernetes, and is definitely the one that has a better tooling built around it. It may be not the best container mechanism for all the use cases, though. OK, now we cleared the concept. Let's practice. I have a multi-node development environment that is running in the office in Menlo Park. There is a private registry deployed on it, and all my containers have the pull policy set to always. Now, what we're going to do is to try to authenticate a subscriber through deployment of SIBA. We'll find an error, we'll fix it, we'll update the environment, and we'll finally authenticate this guy. So just to set a little bit of context, I think most of you have seen the SIBA demo or are familiar with what I'm going to say. But basically, we are going to send EPOL packets through the data plane. We bring them up to ONOS, out to a Redis server. ONOS notice that we provision the flows down in the hardware through a call that comes from the orchestrator. And at that point, we can go out to the internet. Now, this translates in this set of calls. Radius server sends a packet. ONOS noticed that that packet was carrying the information that authentication succeeded. ONOS relied that information on the Kafka bus. The AT&T workflow driver picks that event up from the Kafka bus, and kick off a chain of events that will push all the appropriate flow in the system. So, by chance, I have a read environment. My own use have been discovered. I can start sending authentication requests. They'll go through, but something will break during the push of the flows. So now name is doing is a thing, but if I move here and make maybe the font a little smaller, I can go pick at the logs of the component that I know is going to broke, and we see, hey, we have an error in the code. It happens. I know it's bad. So we need to debug this. We know where that issue is in the file, but we had a unit test. We were pretty sure everything was working. We can check again. Everything seems like it's going. Nothing broke yet. It will eventually complete the unit test. So what is the thing we'll do at this point to solve this issue? Generally, my first approach is go back to the logs. Let's see where our error was. We see multiple times this log because there is a mechanism in XOS that will keep retrying failed steps. This is the file that is causing my issues. So I'm just going there and check. I'll take a look. I think it was line 40. Oh, yeah. There definitely something that shouldn't have been there. So I fix my issue. I'll just go and build. Just go and build my container. Takes a few seconds because it's using the Docker cache to build all that it needs. I'm going to tag it. I'm going to tag it, and I'm going to push it. At this point, my new container is available on the pod. We can check that XOS keeps saying, I cannot synchronize this data. There is an error somewhere. Given what we've said for the pull policy, I just go and delete the pod that was failing. Now Kubernetes is restarting the system. As soon as the new container comes up, code will start going through. We'll get finally our, this is the new container that came up. And now finally, our service instance has been correctly synchronized. At that point, I can go ahead with my test, with my development. I can ask for an IP in the system, and my pod is up and running. So back to the presentation. This is about all that we wanted to demonstrate today. If you have any question, please feel free to ask. So, no question is generally a very good or a very bad sign.
So I take it, Matteo, there is nothing that we can set up in Helm that would automatically look for new images and pull them without having someone have to manually intervene and either delete a pod or do an upgrade?
That's a good question. I don't think Helm provides you such capability. I'm pretty sure it will be not too hard to write a small component that watches the Docker registry, notice the new image, and restart the pod that are using that images. I think that is going to be really tricky to manage it, because many times you may want to push an image to the registry but not start using it immediately. There are for sure tools, but Luca knows much more about that let you perform migration between different versions of the services like Spinnaker. And even with native Kubernetes, we have seen this morning during the keynote, you can iterate through different versions of the same component.
OK, any other questions? All righty, thank you, Matteo.
Thank you, guys.